Okay, today we're going to talk about section 1.3, the division algorithm. This is just a remarkably useful result. We use it frequently, and it all really stems back to something you learned in elementary school. So back in the day, at least for me, I would have written something like 21/5, and I would have changed this to a division problem that looked like this. How many times does 5 go into 21? And I would have said, well, it went in 4 times evenly. And 4 times 5 is 20. And there was a difference of 1. And then I would have said, well, then the remainder was 1. Now, what this really means for us is that you can write 21/5 as 4, went in 4 times evenly, and then there was a remainder 1 that didn't divide out, so 21/5 was the same as 4 plus 1/5. Now we're going to be mostly interested in integers for a little bit, so I don't want to phrase this in terms of rational numbers, so you can multiply by 5 everywhere and change this to 21 is 5 times 4 plus 1. And this is the version of what's called the division algorithm that goes through and is very useful for integer arithmetic. So here's the statement of the theorem. It's called the division algorithm, and it says for any numbers a and b that are integers that are at least 0, also called natural numbers. So a and b are natural numbers. Also, b has to be non-zero. So for this, you should be thinking we're setting up something that's essentially like a over b. So the big part is that it's a two-part statement. There exist unique integers q and r. Here you should think of q standing for quotient and r for standing for remainder. That satisfies two properties. The first is very similar to what we saw up here with 21 being 5 times 4 plus 1, that you can write a as b times q plus r. In other words, b went into a q times. And also r is supposed to be the remainder, and of course that means it should be at least 0 and no bigger than b. Of course, in fact, it has to be strictly less than b, or else you could put b into a more times. So that's the statement. Any a and b bigger than 0, the thing you're dividing by, b, should be non-zero. You can write a as b times q plus r, and the remainder has to be between 0 and strictly less than b. The example, of course, is the example we just did. If a was equal to 21 and b was equal to 5, then you can write 21 as 5 times 4 plus 1. Here the 4 is the q and the remainder is 1. And anyway, that's a unique way to write it. All right, the proof really only has one trick to it, and if you're making notes, if you record this one trick, the rest of the proof will follow just from starting this way. So here we go. The trick is to let S be the following set. It's the set of all x's so that a minus bx is bigger than or equal to 0. You should think of this as all the multiples of b that you can subtract and still have something at least 0 left over. Clearly what we're going to do next is let q be the biggest element in here, and that will be our quotient. Now, to take the maximal element of a set is usually a problem, and most sets don't have maximal elements, and this can be either because if you're thinking of the real numbers, maybe the set is unbounded or the maximal element is not in there. However, This is not the case with sets of integers, at least the ones that are bounded above. So first of all, let's note this. To get things rolling, S is not the empty set because obviously 0 is in there. Next, I claim S is bounded above. If you look at this relation, you can see it's bounded above by A over B. If you want to get a bound that's an integer, that's pretty easy to do from here. But anyway, it's bounded above, and the special thing about the integers is that sets that are bounded above always have maximal elements. That's called the well-ordering axiom, and we can see that in previous sections. It's a property of the integers. Okay, once we have a maximal element, let's go ahead and name it. Obviously, we're going to call it Q. Once we have Q, then we just define R to be what we need it to be. So, as a result of these two definitions, we get for free the following two conditions. Just by the way we defined R, we get cheaply A is equal to BQ plus R, and by the fact that Q is an S, that means these differences A minus BQ are at least 0, so the R is at least 0. So to get the existence part of this theorem, which is half of the statement, we just have to show that in fact this R that we wrote down is strictly less than B. All right, so this kind of yells for us to do a proof by contradiction. So suppose that R was not less than B, and let's see what happens. Well, if R is bigger than or equal to B, we can just use the definition of R, which is A minus BQ, and this would have to be bigger than or equal to B, which is the same as saying if I subtract B, it's bigger than or equal to 0. Now gather the B's together. So A minus B times Q plus 1 is bigger than or equal to 0. But by the definition of S, that means Q plus 1 is actually an S. But if Q plus 1 is in S, this is a flagrant violation of the fact that Q was the maximal element of S. So, since we've gotten to nonsense, that means our supposition up here is not correct. And therefore, R is strictly less than B, and we have existence done. Okay, so now that we know that we can write A as BQ plus R, with R between 0 and strictly less than B, now we need to know that it's unique to write it this way. So suppose possibly that we could do it in another way. So we have our original writing of A as BQ plus R, with R between 0 and B, and suppose we could also do it with a Q prime and an R prime with the same inequalities. So, of course, now let's just subtract. So we get this, and let's throw the R's to the other side, like this. And at this point, we want to notice the following, that since R is between 0 and B, and R prime is between 0 and B, the farthest apart they can be would be if one of them were 0 and one of them were B minus 1, so we get the following, that the absolute value of the difference between R prime and R is strictly less than B. So let's come over here to this and take the absolute value of both sides, and then use this inequality to give us the following. So the R's are at most B with the strict inequality, and the right-hand side, since B is positive, we don't, or non-negative, we don't need the absolute value sign. We get B is strictly bigger than B times Q minus Q prime. If we divide out by the B, we get 1 is strictly bigger than Q minus Q prime. But this difference here is an integer, since these are integers, and the only integer that's strictly smaller than 1 in absolute value is 0. So in fact, q minus q prime has to be 0, which is the same as saying q has to be q prime. And then once you have q being the same as q prime, then over here, this side is 0, for instance, so also you get the r's are the same as well. R is r prime. And that's uniqueness, and you're done with the statement. Or I guess the proof of uniqueness. Okay, that's essentially the only result of this section. I'll state kind of quickly that you can do this for all integers, a with b non-zero, and you can either adapt this proof or use this proof, but I'll go ahead and just state the theorem here. But mostly the theorem we just proved is the one we actually end up using. So the theorem is for any integers a and b with b non-zero, then you can find a unique q for quotient again, r for remainder, so that you have the following two properties. And again, it's the existence and the uniqueness is important. Number one, a is equal to bq plus r. And remember, think of this in terms of your original grade school math. It says a divided by q is b plus remainder of r. And number two, the remainder term is at least 0 and strictly less than the absolute value of b. All right, that's it for 1.3.